Okay, so in a moment of madness, I promised that this should be accessible to people without knowledge of quantum computing. We'll see how that goes. Okay, so but let me start with the basics about quantum computing at least. So here is the main takeaway from quantum computing. Quantum systems are exponentially complex, meaning if you have a system of n particles or n qubits, classically you can describe the state in order n parameters. Quantumly, you need exponential in n parameters. Okay, this is where the exponential power of quantum computers comes from. It's a little more complicated than that. And
the classical statistical system, you will also have exponential.
Yeah, no, that's why I said it's a little more complicated than that, and you have to look a little more deeply, and people think about this all the time. Where exactly can you pin down the power? But okay, but I'm just making up a cartoon here. Okay, so let me also say, if you have a system of n qubits, so two-level systems, then the quantum state is a superposition over all possible classical states of the system. So all the 2 to the n-bit strings, and so superposition meaning that you have an amplitude for each possible n-bit string. Or another way of writing it is as a 2 to the n dimensional vector. So it's a unit vector in a 2 to the n dimensional complex vector space. Okay, so now you could say, well, if it's so complicated to even describe the state of a quantum system, why should physics be possible? Now, why should you be able to actually describe quantum systems and understand them? And so the general answer, at least in condensed matter physics, is that the physically relevant states sit in a tiny corner of Hilbert space. And what's this tiny corner look like? Well, it's possibly low energy states, and these are special, and maybe these have succinct descriptions. And in fact, there's an algorithm which is extremely widely used in computational condensed matter physics. It's called DMRG, invented about a quarter century ago, and it's been extremely successful in solving systems, 1D systems, so systems where you have n particles on a line with, let's say, nearest neighbor interactions.
You would say what solving means.
Yeah, I'll say what solving means. Okay, so it quickly outputs a compact representation of the ground state or low energy state. It doesn't always work. So there are artificially hard examples known where it sort of bounces around and doesn't really do very much. You could draw an analogy here with the simplex algorithm for linear programming, which was, again, extremely successful. It was solved a central problem. There was an example by Klee and Minty which showed that actually it does take exponential time in the worst case. So it was a major embarrassment for theoretical computer science until eventually Katian solved it in polynomial time with the ellipsoid algorithm. This was announced to all the world by the New York Times as showing that p equal to np. But this led to another embarrassment, which was that Katian's algorithm was polynomial time, but it was clearly not very useful for solving linear programs, whereas simplex was. And then eventually Karmarkar sort of set the record straight by actually coming up with a provable algorithm that actually also worked well in, sometimes beat the simplex algorithm. It was sort of right. Okay, so let's go back and look at this question that DMRG solves. Okay, so I'll describe this problem in several ways. For the complexity theorists, it's really the quantum analog of a constraint satisfaction problem. So you're given n particles, so n qubits or qubits. So I'll think of them as qubits, d-level systems.
That means I can take this state.
Yeah, each takes one of d values, and in particular, if you have n particles in a line and the interactions are not just nearest neighbor, then you can sort of make super particles which are bigger and then just make it nearest neighbor. Okay, so now the system is described by an interaction Hamiltonian, which is nearest neighbor. So you have a term for every adjacent pair, and this Hamiltonian is each term of the Hamiltonian is just a d squared by d squared Hermitian matrix. Okay, so each such term is the quantum analog of the constraint from a CSP problem, and what it does is it assigns a penalty of lambda I to an eigenvector EI of H.
Sorry, so just maybe I'm missing something. So D level means log D qubits.
Yeah, yeah. But it's just it's not log D qubits. It's just right. It would be the same thing as.
But why is it then D squared?
Oh, it's d squared because it's two of them.
Oh, got it.
But it's a constant. We should think of
Yeah,
this
yeah.
is a constant.
This is a constant.
I want to just add to Sanjeev's question or amplify Sanjeev's question that for people not familiar with the seminar, it's a seminar where you ask questions about anything you don't understand.
I thought I was supposed to speak less than half the time.
You're speaking exactly as much as the audience is not.
So then I have a question. The boundary conditions on the side, is this just, does it matter or not?
Well, you can make it, yeah, it doesn't matter. It doesn't, yeah. Or it probably matters a lot, but to us it doesn't matter. Okay, so, and then the energy of the state is just the sum of all the penalties. It's just like the classical CSP. In the classical CSP, it's a special case when the HIs commute and they're all diagonal in the same basis, let's say the computational basis. Okay. So what's the complexity of this? Well, okay, so you see the correspondence between local Hamiltonians, constraint satisfaction problems. Energy corresponds to the number of unsatisfied clauses. The ground state corresponds to the optimal solution. Low energy states correspond to near optimal solutions.
So the expression on the right is some logical expression
Yeah.
and then the variables are classified.
Are really Boolean variables. Okay, so that one's NP complete, and this is QMA complete to approximate the energy to within 1 over poly n. And that was Kitaev, and then Gottesman.
Could you explain again, that the H's are all diagonal? Why do you get the CSP problem?
Oh, if let's say that they're diagonal in the computational base, you may as well assume they're diagonal in the standard basis, and then they are just assigning penalties to strings locally. So let's say it assigns a penalty only if that clause is not satisfied. So
Maybe it should be worth clarifying that plus is a funny plus, right?
Yeah.
which plus?
Between the Hamiltonians.
Actually,
It's not d squared by d squared plus.
yeah. No, I'll get to that. I'm going to explain that. But for now, I'm just saying, you add up the penalties, but then I'll explain as operators what it means to add them up. Yeah.
So we assume that the H is commute?
No, only in the classical case they do, but in the quantum case they do not, and that's where the difficulty of the problem comes from.
So, and we want the counting problem. So you're saying this is sharply complete, or we want to know if there is the.
No, we just want to estimate the energy. It's like saying it's like maxsat. You want to say what's the maximum, minimum number of unsatisfied clauses, right? And you want to approximate the minimum number of unsatisfied clauses. So it's that's the same as approximating the energy.
So each of the HIs are really nearest neighbor interactions, right?
Yeah.
So they don't commute, and they're not really D by D matrices. They're D by D matrices tensored with a huge.
Yeah. Absolutely. Yes.
So on the left side, I would know how to talk about excited states, which are min-max problems. On the right-hand side, what would be that?
No, here we are just talking about finding a state which is close to optimum.
Sure, right.
In both cases.
Okay.
Yeah.
Okay.
Okay, and so now it actually turns out even to be QMA complete for 1D Hamiltonians, and it's hard even for translationally invariant 1D Hamiltonians. So it's really this was seen as sort of evidence that maybe maybe these problems are really hard, and DMRG maybe it shouldn't 1D. So the physics intuition was 1D problems are easy, and they seem to say they're really hard.
So maybe not everybody knows QMA.
Yeah. So let me say the conjecture is, if something is QMA complete, then there's not even a sub-exponential size classical witness. Meaning, certainly you cannot come up with a compact representation of the low energy state, but you can't even come up with a sub-exponential size representation of any kind. Not the usual kind of representation of states, but just any kind of hint about what the energy is. That's what the conjecture would say. It's a very strong conjecture. Okay, so now let me just say what these are like, in linear algebra terms. So again, you have these local terms. Hi acts on the entire space as Hi tensor the identity on it acts as identity on everything except the two qubits that it acts on non-trivially. And now you interpret H as H1 plus H2 plus Hn minus 1 as these guys. Right? So each of these is an operator on,
What is this D-n?
Oh, d to the n, because they are n qubits, so they live in a Hilbert space of dimension d to the n. Right? So now in these terms, what we are asking for is an eigenvector with small eigenvalue. So we are given this d to the n by d to the n matrix implicitly, specified by these H sub i's. Okay? So there's a compact representation of H as summation of H sub I, and we are asking for a compact representation of the low energy states, so the eigenstates with small eigenvalues.
So the HI, you can pick anything you want, or there's some Hamiltonians that you want?
It's just Hermitian matrices.
But you mean, so the result should apply to any Hermitian matrix? Well, why these matrices have nothing to do with physics? Or, is that the issue of actually having...
No, so if you depending upon what kind of physics you want, you might even want them to be translationally invariant, in which case you want all the HIs to be equal. Right. But the problem makes sense even in general, and it's not that much more general. It's.
You can manufacture anything that's wrong.
Yeah. Yeah. Okay, so of course that begs the question: why should these eigenvectors have compact descriptions?
Does one really want to describe each eigenvector or linear combination of eigenvector with small energy?
Well, yeah. So it could be any of these, and of course, once you restrict yourself to a small enough dimensional space, then you can do linear algebra there. So if you find almost eigenvectors, you can refine them.
I think one has to explain what you mean by compact description. Of course, they have a compact description. The Hamiltonian describes them perfectly.
Yeah. I was hoping nobody would say that, but now that you open up the can of worms, this is one of these descriptions which is perfectly accurate and completely useless. Yeah. So what we want is a description that allows one to compute the quantities of interest quickly, such as energy and correlation functions and so on. And so what one wants is an honest to goodness compact representation. And I'm just going to finesse that by just describing what I mean by compact representation. right? So what do I mean by complexity here? Okay, so again, we want to say, well, these states sit in a tiny corner of Hilbert space, and we want to understand what this tiny corner might look like. So there is one corollary, though, of this fact, which is that there's this tiny corner of Hilbert space which may have compact description, but most of it does not. Almost all of it does not. Which means that if you're going to use one of the standard algorithms for finding, small eigenvalues, that's not going to work. So if you're using the power method, for example, then you're going to step through this space, and most of the places in this space you really cannot even step through because you can't even describe them. So we have to do something different here. We cannot, even though it's this linear algebra problem, it's really constrained by this fact that we need compact descriptions. Okay, so now let's go back and ask, well, what's this measure of complexity that we want to apply? And it's going to be something very particular. Of course, you'll see that there might, in principle, exist other compact descriptions which might be perfectly fine, but this is the natural one. Okay, so to understand this, let's just understand something about quantum states, which is that the exponential complexity of quantum states is due to entanglement. And probably the simplest example of entanglement is this entanglement of 2 qubits in what's called a Bell state, which is a maximally mixed state, maximally entangled state, where the 2 qubits are in a superposition of being in the state 0, 0, and 1, 1 with equal amplitudes. Okay, this is a famous state for many reasons, not having to do with the complexity because it's too small an example, but it's an example of a state where you cannot describe the state of either particle, but you can describe the state of the entire system. So the entire system is in a perfectly definite state, but neither of these components are. Okay, but now let's say we had our n particles, n qubits, and we divided them into the left half and the right half. And we put them into this kind of a cat state. Just like the 0, 0 plus 1, 1, except now it's a superposition over all possible states I of the left of I. Right, with some amplitude c sub I, which, okay, so in the usual cat state, all the ci's are equal, but we could let it be anything. So let's call it a generalized cat state. Right? So this is a highly entangled state, and you can see that you need a lot of coefficients to describe this state. Now, of course, this comes back to your comment earlier that entanglement is somehow, in some ways, similar to correlations. This could be classical and a correlated distribution, but of course, then there are points of departure which really make them very, very different. I guess one thing that's worth noting is that in some ways, many of the things one talks about here with respect to quantum systems, they can be borrowed and have been borrowed for use in machine learning, because they're ones dealing with probability distributions and inference over probability distributions. Okay, so now it turns out that this picture of this generalized cat state that's really all you need to know about quantum states, because if you have an arbitrary quantum state and you divide up the particles into 2 parts, not necessarily in the middle, then what you can do is a singular value decomposition, which is called a Schmidt decomposition in this context, where what one can say is that look at this left space, right? There's a d to the k dimensional vector space for the left, a d to the m dimensional vector space for the right. And now the claim is that there must be an orthonormal basis for the left space and an orthonormal basis for the right space, so the a sub i's and the b sub i's, such that this this state psi can be written as a generalized cat state in these bases. So it's, if it was AI bj, then this would be just a general expansion, but we are doing a Schmidt decomposition, so it's just AI being paired up with bi. Okay. And now this gives a very natural measure of complexity, which is the number of non-zero terms in this expansion. Okay. So now, certainly if all these AIs and BIs had compact representations, and if the Schmidt rank was low, then you can represent psi efficiently. It has a compact representation too. Okay? Yeah.
Do you need the cut to be roughly in the middle, or?
It can be anywhere.
So this can have very different sizes too.
Yeah. Yeah, and then, when you do this singular value decomposition, you will sort of run out of terms.
Well, it's natural to do it in the middle.
That's one place you could do it. But what we plan to do is make this decomposition at every possible cut. Right? So we just go, at every cut along the way and ask, how big is this decomposition? And we're going to claim that if psi has low Schmidt rank across every cut, then in fact it has a compact representation.
Every cut means every partition, or every cut in this linear?
Well, since we are talking about 1D systems, we'll just talk about every cut along the way, right? So there are n-1 cuts.
The unbalanced cuts will have low rank just by default.
The extremely unbalanced ones, but it could be that there was a relatively unbalanced one which had higher rank than something in the middle.
Well, now, if you had an extremely unbalanced situation, then you'd still have a large number of possible values for B, let's say.
Yeah. But then the number of non-zero terms would be bounded by the dimension of the small side.
But are you supposed to allow to choose anything for A and anything for B?
It's just an orthonormal basis for, so basically so behind the scenes what we're doing is we are writing out the state in its general form. We write it out as a matrix. It will be a rectangular matrix. And then we do a singular value decomposition. And that singular value decomposition corresponds to performing a unitary transformation on the left and unitary transformation on the right space. And what that means is we are picking an orthonormal basis on the left and one on the right. And now our state looks like just a diagonal which corresponds to just that.
So Umesh, the last line, even though it's not highlighted, is the main theorem.
It is a theorem, yeah.
Yeah, no, but it's new and it's the main thing you want to.
No.
It's not the main.
No.
It's all known.
It's known. It's known. Yeah.
Okay, but you need to explain what the tensor network is.
No, I not for the talk, and this is one of the things I'm finessing because there's too much to.
Okay, so it's just something we should know. If it's across every cut there is a low rank,
then that's
a good representation.
Yeah, and then that's just to make sure that people know I'm talking about what's known.
Like polynomial. So the representation is polynomial in the Schmidt rank?
Yeah.
So if one has this low rank for whole cut, will it imply that you can start in the middle, you have AI and BI, and the AI itself, you got in the middle and so on?
Or you could just go from left to right. It's all, yeah.
And why is that representation good for doing things?
It's it allows you to, tensor networks are just linear algebra and pictures.
I understand. What I mean is, what do you want to do with this representation? You said you're not going to talk about it,
but you can do linear algebra with it. That's the main thing, right? You want to do. You want to take inner products. You want to take.
And why is that? So what's the
I'm sorry.
Compute the energy, for example.
Yeah.
Energy is, what is energy? In terms of linear algebra?
Energy would be this sort of. You take the bilinear form and.
Oh, I see.
if you know a compact representation.
For psi,
Yeah.
you can compute it.
Yeah.
For local Hamiltonian.
For local Hamiltonians. Yeah. Because it's local. So when you take this bilinear form, you would take it with respect to one of those, and then almost everything would just end up sort of annihilating each other, except at that local term, and you can deal with that, right? So it'll end up being a constant size computation.
Is there a contrast to this statement that if you have a tensor network, you get low rank?
Yeah.
Yeah.
Yeah. Okay, so in 2006, Hastings proved sort of a groundbreaking results showing that if you have a gapped 1D Hamiltonian, gap means that the difference between the energy of the ground state and the energy of the first excited state is some constant. Right? So I'm assuming each term of the Hamiltonian has norm 1. So this constant means it's sort of proportional to the energy of one term. Then, in fact, the ground states have compact description. The unique ground state has
Nobody gave a polynomial time algorithm.
No.
There was no just the description.
Just that the description is
This is for
compact.
the individual Hamiltonians. Individual Hamiltonians, like the HIs have to be gapped?
No. H has to be gapped.
Oh, the H.
But anyway, it doesn't contradict anything about QMA completeness, because there you want approximation up to 1 over
Poly.
So
Yeah,
this gapped assumption changes.
exactly.
And these are the most interesting systems are gapped, or what's?
Well, what you want to do is study these as the gaps become small. But does small mean 1 over Poly or constant? Probably the latter. But you want the gap sort of shrinking to 0. Okay, so because you want to study systems close to criticality, where
I understand, but in those systems that people study,
Yeah.
Are they gapped?
Well, they
Are they closer to being constant gap, or are they closer to being 1 over Poly? There's a big difference, right?
Just varies system to system.
yeah.
Varies from system to system. depending
Yeah, I
on-
understand, but I'm just wondering how general it is for interesting systems.
I think this is considered the reason that these systems are not like the systems which are QMA complete are not the realistic ones.
So the Brushin's paper is realistic,
I mean, somehow I'm contrasting to the classical situation, where of course this generalizes. In the classical situation,
Yeah.
it's not gapped.
So it's true. In the classical situation, actually, it's degenerate ground states, but it is gapped because you have a discreteness about it, right? So
But
if the
it's
energy is
far
not
away. I mean, it's
no, it's so it's if the minimum the optimal solution leaves 5 clauses unsatisfied, then the next from optimum, if it's not 5, is going to be 6. So there's a gap of 1. That's what gap means.
you normalize. So this is the sum is like n as
Yeah.
opposed to 1. I got it. Okay.
Yeah. Actually, so after Hastings' paper, I skipped that reference, but there was a paper which sort of suggested that maybe these even such states which satisfied area laws, which proved that they could be as hard to compute as factoring. Okay, so there was some thought that maybe these were hard, but then it turned out that intuition was incorrect, and then actually with Landa and Vidic, we gave a polynomial time algorithm to find such ground states in such systems.
Do you find exact ground state or like
Close to, because the ground state itself may have very high entanglement rank, infinite entanglement rank, or very exponential entanglement rank, but its entanglement entropy is small, which means you can very closely approximate it with small rank, and so that's what this does. But this was, you know,
For GAP.
this is for GAP.
You raised the requirement of GAP, but you should have.
With this,
Okay, yeah.
with this GAP. So, but this was, you know, it was a polynomial time algorithm in the genre of the ellipsoid, in the sense that it was polynomial time, but you don't want to implement it. Okay, so it had two problems. There were two problems here. Well, it's not practical. This was not practical. And secondly, what about low energy states? You know, do they have compact descriptions? Can you find them? Right? Yeah.
So I think there's a paper by Kitaev and others on the archive, at least, which claims to prove a sub-exponential time algorithm for ground states. Is there a mistake in that? Or
No.
Okay.
No, that was a precursor to this.
Yeah. Okay.
So
I was wondering. Okay, what did it say?
I'm sorry.
Got it. Okay.
Okay, so let's go ahead and examine.
What do you mean by low energy?
Yeah, I'll describe that here. But for the moment, let's just think of it as something close to ground state. But I'll make that precise in a moment. But let me just say why. Okay, so let me start by just considering degenerate ground spaces. Okay, so instead of having a unique ground state, let's say that the ground space has dimension polynomial in n, and then it's gapped. Right, so it's exactly like the gapped local Hamiltonian, except now instead of having a unique ground state, there are polynomially many of them, a polynomial dimensional space. They're all the same, so there's no gap there. But then once you get beyond that, it's a gap of it's a constant gap, right? So the reason that previous, you know, these proofs of compact description don't seem to work, and you know, this was sort of a major problem because you know, they fail completely for this kind of a setting, because these proofs, what they did was they showed that for every cut there's some ground state with low complexity, with small rank. Okay, if there's a unique ground state, then obviously you're showing it for that one, and so now you've shown for every cut it has small rank. But now that there's a large ground space, all we know is that for every cut there's some state which has low complexity. So at the minimum, we want to show there's some ground state with low complexity across all cuts. And of course, ideally, what we want to show is that all ground states have low complexity across all cuts. Right? And the point is that while, you know, the way you show this low rank, low complexity, is by, you know, you sort of chase things down, and in the process of chasing things down, you have no idea where you're ending up. Right? You just say you make progress, but you don't know where you end up. Right? Now, what we'll, you know, how will we generalize this? We'll say for low energy states, we'll just replace the gap condition with by saying that they are polynomial and lowest energy states, right? So they, you know, if you look at some constant gap between E naught and E naught plus C, then there are polynomially many states in that range. So we don't insist that they all bunch up near the bottom. They can be anywhere in that range.
I'm still confused. What is called constant here?
Oh, constant. So constant means comparable to the norm of a single term of the Hamiltonian.
how will it compare to E0?
I'm sorry?
And how will it compare to E0?
E0 can be arbitrary. It's
It's of order n.
E0?
Zero can be zero.
Yeah.
It can, but typically it's
Yeah.
order n.
Yeah. Okay, so now we have two problems on our hands. One is being able to establish this kind of compact description for low energy states, and the other is being able to find them quickly. It turns out the solution to both of these is really the same. Okay, so what we want to do, okay, so here's the subspace T of low energy states, let's say. Right? This is not that corner of Hilbert space, it's just for this particular Hamiltonian, the subspace of low energy states. Now, what we'd like to do, this is what would be really nice. Suppose we could quickly identify a small subspace which contains this. So,
Small dimension
of dimension polynomial in n. Right? So now we could restrict the problem to this subspace, and we could, if this subspace is specified by a basis of tensor, matrix product states, we can do linear algebra. And now, since we are doing linear algebra in a polynomially large space, then then it's all easy. Then we can find eigenstates and do whatever we want with it. Okay, so the real problem is, how do we identify this low dimensional subspace?
Subspace means
Just a span of some vectors in C to the D to the n.
but of low Schmidt rank.
Well, we want to represent these vectors efficiently. So we want a subspace of with a basis, with a compactly represented basis.
So each has low Schmidt rank,
Yeah, each has compact representation.
which is low Schmidt rank.
Yeah.
Do you really want normality to be in it or only close to it?
Yeah, so we want it to be close. You're right. Okay, so let's see how we can formalize this. So obviously, finding this thing inside this exponentially large space is hopeless unless we find some more structure to the problem. So let's see how we can work at this problem sort of gradually. Okay, so what's the structure? The structure is that there are these n particles. So what we'd like to do, the obvious thing to do is to somehow start working on a few particles at a time. Right? But now let's try to understand. So let's even say for now that we are trying to find a unique ground state psi. Right? There's a target state psi. That's the only one we are trying to find. Now, and we want to start working on this, on these first few particles. What should we keep around? So we are making progress towards psi. Okay, so in other words, there's of course the fact that psi is unknown. So how could we even know what to keep around? But suppose I even give you psi and you say, look, you pre-process it, you figure out what you want to keep around just to tell me you're making progress. Right? You know it behind the scenes. Just tell me what you'd like to keep. Well, even under those circumstances, what you want to keep around is not a state, but you actually want to keep around a subspace. Right? Because when you take the state psi and you cut it at this point, the best thing you can do is a Schmidt decomposition. But then you want to keep Schmidt rank many vectors on this in this space. Right? So you're keeping a subspace of this Hilbert space. Right?
So just knowing that first part, you can reconstruct the second?
I'm not saying any such thing. I'm just saying, I mean,
it's a minimal.
Yeah, this is extremely minimal. This is just
necessary, not case.
Yeah, far from, right?
You want to keep the AIs with small CIs, even though you don't know
large CIs.
Large CIs.
Even though, yeah. But we don't, but we know nothing here. We don't know the CIs, we don't know the BIs, we know nothing at all. But so it really does seem hopeless, but let's keep going anyway. Okay, so let's keep going and make up a definition. Okay, so let's say now that T is the target subspace of low energy, right? So this is the subspace we want to reconstruct. So ideally, when we process these particles A, we'd like to identify a subspace S of T such that we haven't yet, it's not hopeless yet, right? So if we keep around S, we want to make sure that T is contained in S tensor X, right? So we haven't yet lost the target subspace. And now we want to say, of course, that we don't want to keep reconstruct T exactly. We just want an approximation to it. We just want some overlap with it. So turns out a good way to say this is we'll say that this subspace S is delta viable, okay, if the following holds. If you take the projection onto T, this is the projection onto S tensor X, projection onto T, it's at least 1 minus delta projection onto T. Okay. Delta is the error, 1 minus delta is the overlap. Right? So what we want is we want dimension of S to be small, delta to be small, so that, okay. And now let me let me give you an interpretation of this. Okay. The interpretation of this condition is, it's actually a pretty strong condition. What it says is, if you look at the unit ball in S tensor X, then when it's projected onto T, it contains a ball of radius 1 minus delta. Okay, so let me say why this is a strong condition. What it's saying is, for every element of T, so for every low energy state, there's some element in S tensor X such that when you project it onto T, you get exactly that element, nothing else in T. Right? It has zero. You project, you get something in the direction of this state, except that you don't get it exactly. You get 1 minus delta. And then, of course, there could be components. So what that means is that the state in S tensor X, it's a superposition of this element of T and something outside of T. But among the low energy states, that's the only component it has. Right? The fact that this is true, this is what makes the algorithm really work. Yeah.
Sorry, one quick clarification. S is a subspace of A.
I'm sorry?
Is S a subspace?
Yeah, S is a subspace of the Hilbert space. So I'm thinking of A as the Hilbert space here. So if you take these three particles, the state is a vector in a D to the.
And T is a subspace
3.
of the Hilbert space of A tensor X.
Yeah. Sorry, T is a subspace of the entire Hilbert space, A tensor X. Yeah. Okay, so let me just say a couple of things about viable sets. So first of all, we'll think of S interchangeably either as a subspace or as a compactly represented basis for that subspace. So that's why we think of it as a set. It's a set of vectors that form the basis, but it's really a subspace spanned by them, and we'll go back and forth between them. Delta is the error, but sometimes it's more convenient to think of the overlap with this low energy space, which is 1 minus delta. And the other thing is, it would seem that a viable set is an extremely non-constructive. You certainly cannot test whether a set is viable or not. Right? In particular, we don't even know what the target looks like. So how could we even test? But
just the existence of a small dimension of such S is guaranteed by the fact that
No, but we don't know
by
that.
the fact, sorry, by the fact that you assume that T, the lower energy state, is lower dimensional.
No,
It's
no,
ca-
no.
It's not even.
No, because see, even if T was, even if there was one vector in there, it could be a highly entangled vector, and then it could be a highly entangled.
You know it's not entangled.
No, so
don't you assume the assumption about the Hastings theorem doesn't give it to you?
no, because Hastings only showed that for a unique ground state, right? In a gapped.
So in a unique, it would be going.
In a unique, it would be.
So you have unit. In particular, you extend.
Yeah. So
without to polynomially.
Yeah. Right.
dimensional.
Yeah.
Lower energy state.
Yeah. Okay, so now, even though this is, this doesn't seem like a very, a testable concept, so how would you use it in an algorithm? In fact, I would claim that this is a very natural way to think about algorithms for such, such systems. And the reason it's such a natural thing to think about is because there are many algorithmic primitives we can give for viable sets, for how to combine them, how to manipulate them. And once you have these primitives, you can combine them into an algorithm. Okay, so let me describe some of these primitives. So let's say that we find a viable set for A and a viable set for B. So S1 is delta 1 viable, S2 is delta 2 viable. So now we can take the tensor product of S1 and S2. And that's going to be delta 1 plus delta 2 viable. Okay. So the error went up by a factor of 2 roughly. The dimension squared. Right? So we might try and say, well, what happens if we convert this into an algorithm? So we start with n particles. We have a viable set for each, the trivial viable set, which is take the entire subspace. And now we start combining them by tensoring. And of course, we get the entire space, so this is quite useless. So we need some way of reducing the dimension, because we can't afford to keep multiplying the dimensions up. Okay, so here's another primitive, random projection. So what you do is, suppose S is a delta viable set, and dimension of S is little s. Okay, so it's delta viable, meaning the overlap is 1 minus delta. So now what we can do is we can just sample uniformly at random a subspace of S of dimension little r. Think of little r as much smaller than little s. And so what it does is, with by a concentration type lemma, with a little bit of work, you can show that in fact r has overlap about 1 minus delta times r over s.
This is delta now.
Yeah.
I mean,
I'm sorry?
it goes away from 1.
Sorry?
It looks really bad for the error.
Yeah, it looks bad for the error, but at least the size is not bad. So again, we can try this algorithm again, and this time the size is completely fine, but by the time you get up there, the error is exponentially small, and it's just it's a disaster. Okay, so now there's a third primitive. It's called error reduction, and this is where all the magic happens. So suppose S is delta viable. It has dimension little s. Oh, error reduction, not boosting.
It doesn't have much to do with actual boosting? Or it does?
No.
It's not nothing to do with.
No, nothing like that. Okay. What it does is it yields another viable set S prime, which is capital delta over 1 minus delta squared viable. I haven't told you what capital delta is yet. So that's going to be something to do with this error reduction process. And the dimension of S prime is going to be d squared times S. Okay, I haven't told you what d is either.
You say d squared.
I'm sorry?
You say d squared.
Yeah. D squared times S. Okay. Now, the way this error reduction is carried out is by applying, this is finally where we take the Hamiltonian into account. So we use the Hamiltonian to create an operator. And that operator has two parameters associated. So that operator is called an AGSP. It's an approximate ground state projector. Okay, so we use the Hamiltonian in order to okay. So we use that operator in order to we use the Hamiltonian to design this operator, and we want two properties from it. One is that let me
It's an operator where,
I'm sorry,
on what
on the entire Hilbert space, right? And I'm going to assume that I'm working with the case of degenerate ground space, so polynomial degenerate ground space with a gap, because that's the easiest one to talk about. So now this AGSP is going to satisfy the condition that the operator fixes every element of the ground space. Okay, and everything orthogonal to the ground space, it shrinks by a factor of delta. Okay. At the same time, if you look at the two cuts at the two ends of this interval where we are finding, for which we are finding the viable set, then on each side of the cut, this operator has rank at most d. So if we were to cut the operator in these 2 points, right, we could write the operator as ai tensor bi tensor ci sum over I, where I goes from 1 to d squared. Right? So there are d squared terms in this operator.
Sorry, what is capital delta again?
Capital delta. So remember I said this AGSP is an approximate ground state projector. What that means is it fixes the ground space, right? So it's an operator k such that k times any vector v in the ground state is v. But now if you apply k to anything orthogonal to the ground space, then that vector shrinks by a factor of at least delta.
This is what you expect the original Hamiltonian to do if you just shift, right? I mean, if let's say the bottom energy state was 0, then identity minus the Hamiltonian will keep the low ground state where it was and shrink everything by the gap.
By something, yeah. The gap now being normalized, so it'll be 1 over poly, 1 minus 1 over poly. But now we want a much better such shrinkage. Right? So we want to take the Hamiltonian and massage it into an operator which is much more efficient at doing the shrinkage compared to the complexity. Right? So we are trading these two quantities against each other. And the sense in which it is extremely efficient is that what you pay in d is much smaller than what you gain in delta, in the sense that d to the 8 times delta is even smaller than 1.
This kind of idea already appeared in your earlier work with Vivek and with Itai and Zeph, and with Alexa, with Alexa Kitai. Okay.
You are assuming that you have a gap here, then, or not?
I'm going to assume that I have a polynomial degenerate ground space, and then there's a gap above that, right?
But then, can you use this to prove that you have a gap, or?
No.
You have to assume you have a gap.
You have to assume you have a gap.
You find the ground states.
Yeah.
Okay.
Yeah. And to show that the ground states, every ground state has compact description, right? And then more generally, even if it's not a degenerate ground space, but if there's polynomially many low energy states, then the same sort of thing holds. Okay, so let me say why these three things together are really, taken together are powerful primitive, right? So here's what we're going to do. So suppose we find delta viable sets for S1 and S, for A and B. So call them S1, S2. They're both delta viable, each of dimension S. So now we tensor them together. So we have a viable set for A union B, A tensor B in this case. So S1 tensor S2 is 2 delta viable and of dimension S squared. So we don't like S squared. So we are going to do random projection down to dimension R, where R is small compared to S. Okay, it's I'm sorry?
Small compared to S or
small compared to S. So we see eventually we want to get back to S. Right?
Oh, okay.
So we'll just push it back much farther. Okay, so we'll push it down to R much smaller than S. And now we'll get something that's roughly 1 minus R over S squared viable.
Really? That doesn't seem consistent with the formula you put up there before. It seems like you got a factor R over S outside the 1 minus that.
Yeah, no, so before what I was saying was in terms of overlap.
Yeah, so the overlap would be just like in
The overlap is now going to be very small. So I'm thinking of one, here 1 minus delta is, we may as well throw it away compared to R over S. So R over S is small.
Yeah.
So now if you look at, that's the overlap. So if you look at delta, it will be 1 minus R over S.
Capital delta?
No, little delta. The error will be very close to 1. So it'll be, now what I'm saying is that the error is 1 minus R over S is now S squared.
I see. Viable means the error. I see.
Yeah, this is the error. Right, so the overlap.
Very bad though.
The very bad error.
Yeah.
I'm sorry? It's a very bad error, yeah.
Very bad though.
Yeah. But now we are going to apply dimension reduction. Error reduction. Yeah, sorry. So we apply error reduction, and what we want to do is apply an AGSP so that our dimension gets back up to S. Okay. Yeah, and now we want to figure out what the new error is, right? How viable is the set? So the viability is delta divided, capital delta divided by 1 minus little delta squared, right? Capital delta divided by 1 minus little delta squared. So that'll be divided by R over S squared, which will be, so when we square it, we'll get S to the 4 divided by R squared. And now we now we use the fact that delta times d to the 8th is small to sort of show that this is smaller than S.
Delta times what?
I'm sorry? Delta times
I see.
okay. So basically what we are doing in this process is, what we've done is we've managed to take two viable sets which are both delta viable and then combine them into a viable set which is also delta viable of the same dimension, but now it's viable for this larger system. Right? But once we have this, we can keep going. Right? So now, well, now we can, okay, so if we wanted to, we would now do this stuff, except now we are doing a tensoring and then applying the random projection, then applying the AGSP, and then tensoring, etc. And we do this in a binary tree.
So this gives you control over fixing the dimension of the target subspace and then
Yeah.
finding a good target separate subspace of that dimension.
Yeah.
Because you can choose S and just.
Well, S will have some constraints depending upon the cardinality, upon the dimension of T. It's got to be at least the dimension of T, and probably somewhat larger because of this squaring and so on.
So it has to increase a little bit the process.
No, so we just get it to some value, and then from then on we can just keep going.
Looks very much like zigzag.
So
Like,
Zigzag.
you should talk. Okay, and if you want the tensor network representation, that's what it'll end up looking like. That's your AGSP. You clip it at these points. You apply it. You take a random projection. Do this again, tensor product.
So you'll explain the AGSP.
I'll say a little bit about the AGSP. Just a little bit. Okay, so what are the results? Eventually, when you put it all together, you get a polynomial time algorithm for computing the basis for this poly and degenerate ground space, and it implies an area law. Which area law, it's just how much entanglement there is across any cut, and the area law is basically as good as we know for 1D. So you just add log of the dimension of that subspace to the entanglement bound, the best entanglement bound we know for 1D so far. And then in the case of low energy states, we get a quasi-polynomial time algorithm, and we get an area law up to a log correction. Okay, so I'll just describe a little bit about the AGSP, not very much, because I think I'm probably already out of time.
Is that the place where you cannot take this to higher dimension, or is
Yeah.
it other?
No. This is the thing that we'd like to understand better.
Also, is it really about just the dimension of the Hamiltonians, or it's okay if the interactions are between a few pairs?
If they're local, then it doesn't matter. If they're global, then it's not clear what it means to be 1D. Okay, so an AGSP is just an operator K that is not too complex and approximately projects onto the ground space or ground state, as the case may be. So it preserves the ground space. It shrinks the orthogonal space by some factor of delta, and it has low entanglement rank across the cut. So here I'm thinking about it as across one cut, but you can of course generalize to across multiple cuts. So we'll say that an operator on this tensor product space, if it's of this form AI tensor BI, if there are C terms, then it has entanglement rank C. Right? So we want this complexity in these terms to be low, and we want it to shrink a lot, and there's this trade-off between shrinking and complexity, and that's what we want to control. Okay, so how did we construct? So what I'm describing to you is the old AGSP construction, which was highly non-constructive. Now for the algorithm, we have to make this entire thing constructive. So one thing is making it constructive so that we can do it efficiently. The other thing is in this construction, we completely lose track of the entanglement rank across these other cuts. So what we do is we take the line, we say we are interested in this cut, so let's keep around only a small number of interaction terms around this cut, where small is going to be something like log squared d, d is the dimension, divided by epsilon, where epsilon is the gap. Right? So it's constant, independent of n. So there's some constant path independent of n, but depending on d and epsilon, that we keep around. And then we take everything to the left of it and we call it a Hamiltonian H sub left. Take everything to the right, call it H sub r. Okay, so far, if we call it something, that doesn't accomplish anything. But now, having called it something, we also then say, let's also truncate it. So meaning, we look at the spectrum of this Hamiltonian on the left, and we say, everything that has eigenvalue above a certain point, we'll just flatten it out. So the eigenvalues go up, and then they flatten out. So the norm of this Hamiltonian is now small. Similarly, we flatten out this Hamiltonian, and then we say, doing this flattening does not change the ground energy very much. Right? It doesn't change the ground state ground energy very much. Okay. And so now we have this new Hamiltonian which has small norm because S was small, and then these two Hamiltonians have small norm. And now what we are going to do is we are going to take a Chebyshev polynomial of this H prime, an appropriate Chebyshev polynomial applied to H prime. And that's what this operator K is going to be. Okay. Now, the Chebyshev polynomial, applying it to H prime means we are applying it also to the eigenvalues, and that has a property that it sort of suppresses it suppresses the function in a certain range while increasing it at the fastest rate outside of the range. So what we want to do is take this Chebyshev polynomial, have it at 0 or at the ground energy, have value 1, and any place away from the gap we want it to be narrowly bounded. Right? So that's what an AGSP is. It takes the ground state or ground space and it leaves it alone, meaning its eigenvalue is 1. And then everything above the gap, it really, it keeps it narrowly confined. It has a very small eigenvalue. And the Chebyshev polynomial is the most efficient polynomial at doing this. So that's one aspect of it. The second aspect of it is that the entanglement rank of this polynomial is low. Well, that's not a property of the Chebyshev polynomial. It's just a property of polynomials of degree d. Okay. But now, in order to show this, you have to do some combinatorics to show that you can group terms in certain ways. If you look at the number of terms, it's very large, and the naive entanglement rank is very large. But then we want to say that, in fact, there are ways that you can group them, and in fact, it's something somewhat involved, which shows that, in fact, you can do the grouping in a way that it's
group as in like they're exactly the same. I mean, the basis elements.
No, what you want to do is you want to say, look, you have h1 plus h2 plus so on. You have that raised to power of something. So now you go ahead and expand it out, right? So now you'll get various products, and now you want to say that, in fact, this if you look at any one term, it doesn't have high rank across any cut, right? Across the cut we are interested in. But now you want to say, well, all of them together don't have high rank, and so but there are so many terms that you have to group them, and you have to say, well, you could have gotten this by taking some other product, and it didn't have high rank, and then you piece things together in this way.
So this all goes to prove this the remarkable property, this relationship between capital D and capital delta.
Yeah.
That it's essential to do this and to take Chebyshev and
right.
not some power and so on.
Right. And then in order to really do this for the algorithm, we have to now figure out how to do this truncation well, and so that's another kind of worms. Okay, so there was a recent implementation of a heuristic version of this algorithm by Roberts, Vidic, and Antronich. So what they do is they use a heuristic version of the AGSP, some sort of Trotter expansion of e to the minus kh over t. They replace random sampling by taking the bottom s eigenvectors of a restricted Hamiltonian, and then their implementation is roughly factor 5 to 10 slower than DMRG. DMRG is this very successful algorithm, density matrix we know. Yeah.
So DMRG was doing something similar at the heuristic level, or
no, not at all. Yeah, and in fact, this rigorous RG does better when there's ground state degeneracy, or when you have a low energy space you're trying to reconstruct. So DMRG on hard instances seem to get stuck, at finding a solution, and then trying to get it to get to the other solution is actually not that easy. And here it actually seems to work quite well.
That's something they found.
Yeah.
In implementing it.
Yeah.
These harder instances.
Yeah.
It performs better.
Yeah. Okay, I should say a couple of more things about. Actually, also this was sort of a preliminary implementation, and it's quite possible that instead of using this, one could actually it would take much more work, but there was the combinatorics of that went into showing that this AGSP was good. One could sort of track through that and see how to do a more efficient implementation. That may not be the only place, So they basically programmed this on iTensor, and okay, so that's what this implementation was. Okay, so I should say that there's a special case, frustration-free Hamiltonians with unique ground state. So in that case, the algorithm works in n times matrix multiplication time. But we actually have a conjecture about bond trimming. So as the algorithm goes along, we are keeping track of these basis states as matrix product states, and they have some bond dimension, and the bonds keep building up, and so we have to trim the bonds. And the question is how well can we, what kind of bounds can one get on that bond trimming? So as far as we can tell, our bounds are off by a factor, and if we could get the right bound, then in fact this running time would be almost linear, n times polylog. Okay, and then of course there's some similarity to the renormalization group here. Of course in this case the similarities there are similarities and differences. In the renormalization group you say, well, there's a scale invariance, and often at least you talk about translationally invariant Hamiltonians, and you talk about what they look like at different scales. Here, of course, every term is different, but there's something in this tensor network which is quite evocative, which is that you can apply all the AGSPs. So the Hamiltonian is being applied from down here, and we are just clipping it out at so initially it's clipped up everywhere, and then later we clip it at longer and longer intervals. And then we are doing this random projection up top. But if you actually look more closely at the prescription for the random projection, it actually does take these bonds into account, right? It's actually quite possible that the algorithm works maybe provably without taking these bonds into account, in which case all we are doing is we are applying these these fragments of the AGSP, and then doing an oblivious sort of tensoring and random sampling without really referring to anything. So it would just be, you're just applying these operators which are completely oblivious in the form of a binary tree. And that's